for cosine x and sine x. The same sort of thing. And I should mention that on your homework, you have to do it for cosine of x. I changed my mind on the spur of the moment. I'm not going to do it for cosine because you have to work it out on your homework for cosine. And in a later homework, you'll even do this case. So it's fine. You need the practice. OK, so how am I going to do it this time? This is, again, a reduction formula. And the trick here is to pick u to be this function here. And the reason is the following. So it's very important to pick which function is the u and which function is the v. That's the only decision you have to make if you're going to apply integration by parts. When I pick this function as the u, the advantage that I have is that u prime is simpler. How is it simpler? It's simpler because it's 1 degree down. So that's making progress for us. On the other hand, this function here is going to be what I'll use for v. And if I differentiated that, if I did it the other way around and I differentiated that, I would just get the same level of complexity. Differentiating e to the x just gives you back e to the x. So that's boring. It doesn't make any progress in this process. And so I'm going to instead let v be e to the x and, sorry, this is v prime. Make it v prime is v to the x. And then v is e to the x. At least it isn't any worse when I went backwards like that. All right? So now I have u and v prime, and now I get x to the n, e to the x. This again is u, and this is v. So it happens that v is equal to v prime, so it's a little confusing here. But this is the one we're calling v prime. And here's v. And now minus the integral, and I have here n x to the n minus 1, and I have here e to the x. So this is u prime, and this is v dx. So this recurrence is a new recurrence, and let me summarize it here. It's saying that gn of x should be the integral of x to the n e to the x dx. All right? Again, I'm dropping the c. And then the reduction formula is that gn of x is equal to this expression here, x to the n e to the x minus n times g n minus 1 of x. So here's our reduction formula. And to illustrate this, if I take g0 of x, if you think about it for a second, that's just, there's nothing here, the antiderivative of e to the x, that's going to be e to the x. That's getting started at the real basement here. Again, as always, 0 is my favorite number, not 1. I always start with the easiest one, if possible. And now g1, applying this formula, is going to be equal to x e to the x minus g0 of x, which is just right because n is 1 and n minus 1 is 0. And so that's just x e to the x minus e to the x. All right? So this is a very, very fancy way of saying the following fact. I'll put it over on this other board here. Which is that the integral of x e to the x dx is equal to x e to the x minus x plus c. Yeah, question? I did this in my, the question is, why is this true? Why is this statement true? Why is g of 0 equal to e to the x? I did that in my head. What I did was I first wrote down the formula for g0, which was g0 is equal to the integral of e to the x dx, because there's an x to the 0 power in there, which is just 1. And then I know the antiderivative of e to the x. It's e to the x. Yeah?
How do you know when this method will work? You know, the x and e to the x.
Good question. So let me just repeat that question. How do you know when this method will work? The answer is only by experience. You must get practice doing this. If you look in your textbook, you'll see some hints as to what to do. The other hint that I want to say is that if you find that you have one factor in your expression which when you differentiate it, it gets easier, and when you anti-differentiate the other half, it doesn't get any worse, then that's when this method has a chance of helping. All right? And there's no general thing. The thing is, though, if you do it with x to the n e to the x to the n cosine x, x to the n sine x, those are examples where it works. This power of the log. I'll give you one more example here. So this was g1 of x, right? Was this one? I'll give you one more example in a second. Yeah. Thank you. There's a mistake here. That's bad. I was thinking in the back of my head of the following formula, which is another one which we've just done. All right, so these are the types of formulas that you can get out of integration by parts. There's also another way of getting these, which I'm not going to say anything about, which is called advanced guessing. You guess in advance what the form is, you differentiate it, and you check. Okay, that does work too with many of these cases.